welcome from my side to everyone, and thanks for joining. I hope you find the talk interesting. I will talk about human in the loop, practical lessons for building comprehensive AI systems. So, who is talking and about what? So, I'm Adrian. I'm the team lead for machine learning at Merantix Momentum. I have 5 years of experience in project-based applied machine learning with a focus on computer vision, and I'm based in Berlin. And Merantix Momentum, where I am leading this team. Some news about us. We are founded in 2019 in Berlin, and we do projects for other companies based on machine learning. So we don't have a product. We usually start developing from scratch. So we have a lot of experience in this iterating quickly and building solutions that solve business problems in a very short amount of time. And with this, we are focusing on complex solutions and usually, also with a focus on deep learning. 60 people right now, 14 machine learning specialists, and also currently hiring more. And what I will talk about today is I'll give a deep dive into one of our computer vision projects. I would say one of my personal favorite projects in the last years. Explain a bit motivation behind it. Go and cover the machine learning methodology that we used, and also in general, just talk a bit about the design principles for machine learning projects that we usually apply in our projects, which is a lot data centricity and also user centricity. And in the end, if we have time left, I will also deep dive a bit into the tech stack that we use for this specific implementation. Okay, so what's the problem that we try to solve here? What's the motivation? So this one was done with a company in the pharma space, and they have to do as every other pharma company that does compound development. They have to do animal testing, which means they have thousands and thousands of hours of video data from rats, and they want to know what are these rats doing in these videos. And the corpus of data is too large really for a human to easily go through that, even for a large team to analyze this large amount of video data. And what they are interested in is, on one hand, like what are the behaviors that are shown by these rats. For example, how much do they sleep, how much do they groom themselves, but also then things that you get from this, like how much does grooming happen after eating or things like that. Which I would say is maybe even a bit more of a basic or standard approach of the problem here. So the action recognition or temporal segmentation of a video, where you want to have start and end point of certain behaviors. But at the same time, they also said then, okay, if we test a new compound, it can be also happen that the rodent is showing some behavior that we have never ever seen before. So what we also want to see is completely new and currently or previously unseen behavior, and kind of guide users towards those interesting looking sections in the video. So you can also think about it, if as a human I have 20 minutes of time to look at video data, I want the system to guide me and tell me what are the most interesting 20 minutes that I should look at, and then also get this aggregated statistics out of it, of this behavior distribution, so to say. And now the question is, how can we design an AI system that solves this use case, and what are the principles that we could apply here? And how we think of it is that there are these three aspects for AI system. It's the model-centric part, where you think about which model to pick, which properties should the model have, or which model is really suitable for the case, and how can I fine-tune this model or the training setup to achieve good machine learning metrics. The data-centric approach, which then I would say became much more attention over the last couple of years, where we say, okay, the model is one thing, but even more important is having the right data set to train it on, and clean labels and representativeness of our data set that we train on must be the case. And then I think the third aspect, if you think about building these systems that in the end really solve a whole business aspect, is how do actually user interaction happen with your model. And here then you can think these questions of like, okay, maybe even though normally we think from a model perspective a lot of okay, what is the main prediction from the model, but then you could also think about what about top 2, top k predictions. So maybe it makes more sense to also include those. How important is uncertainty estimation? Should I show that to a user or should I not show it to the user? How safe the or how perceived the confidence of the model is, and even just the user interface where a user interacts the model, and also then things of education of the users. Do they understand what models can do and what can they not do? Like also this aspect I think is really crucial part of building AI systems that really have an impact, and is maybe still a little could get I think a bit more of attention in from the side of practitioners. Then if we show a little bit background here to cover a few terms, also if we think of the human in the loop system, what you usually have at hand is a large pool of unlabeled data, and then also a certain percentage of that which is labeled, which in this case at Project Start definitely was the case with, I would say, I think 1,500 hours of unlabeled data and roughly 30 minutes of annotated data. Then you have the active learning part where you are now choosing from this large pool of unlabeled data, which subset of this data should I send to humans to label it. Here, the first interaction with the human takes place where they are training, creating a training data set by labeling the data. Or that on its own, you can spend a lot of time talking about that, how you ensure that different humans have the same expectation in labeling or show the same behavior in labeling, so that there is no like a large labeler agreement and things like this, and also just to make it as efficiently as possible for them. Yeah. Then now you have some training data. Now comes the part, of course, where you can finally train some model. Ideally, you use transfer learning, so you use a model that was already trained on some similar task or data, just to speed up this training so that you can already get reasonable results with a small amount of training data. Then you deploy the model, you use it maybe for the active learning part. So you choose the predictions from the model to then incorporate into your algorithm of choosing which unlabeled data you select. I think in general, these concepts you could also see in the previous talks about all the things that you could do to select your subset of the data, and then the circle kind of continues. And now coming back also to the slide before, if we then think what were questions that we had during these model or system development part, it's I think one of the most important one is actually what value does the model or the whole system create, and how can I actually measure that over time? Because we also, of course, are interested in proving that this works and that this helps anyone. The system user interface, is it intuitive for different types of users, but then also the labeling process, and how does the model integrate into the client's business workflow? All of this going then more into the model-centric direction of which model architecture should I actually choose, which metrics should we optimize for, can the model scale with more data, or does it not even help if I add more labeled data? So from this large corpus of, I would say, decisions you have to make, and for all of these questions, let's try to answer a few of them, how we did it in that project. Next, I kind of jump to the end of the project and just first show the outcome of the system, and then we dig deeper into it. How does really the machine learning part look like? how do the results look like, and which tech did we choose to implement it. So in the end, this is kind of the user interface that we came up with, where you can see with one view at the bottom the predictions from the model, kind of in this timeline, and then also labels set by the user, so they are in a like more kind of bold or darker highlighted. And this is kind of the fingerprint of a video, where with one glance you can see, okay, here really the rat is sleeping a lot, or it's doing a lot of sniffing. Yeah. And then in this case here, the users, they are also able to retrain the model. So they can now do a lot of labeling. They can also, for example, add a new class and decide that now now they are interested in another behavior type that they didn't see before. They add a new class, they add some labels, and they can retrain the model in the background without having to involve us, or without any machine learning person involved. And then in the system, we retrain the model automatically and then predict again on all the video data, and then the cycle can kind of continue. Yeah, and then one big aspect here in this project, as I mentioned in the beginning, with very little training data, was this: how do I select which data to label? And here we have this smart labeling, smart assistant, where if a user clicks on it, they get pointed to specific parts of the video. The video jumps to those sections, and then the user is basically asked to, for each video, label 40 time points. Yeah, and this is kind of the interaction for the labeling. And we see also the labeling part and the interacting part with the model is kind of connected to each other. So it's not so much, okay, we first do a project where we collect a lot of data, we train the model, we roll it out, we never touch the model again, we never touch the training data again. Maybe even the people who label the data and the people who use the system in the end are different. No, in this case, it's really from the beginning very, very combined. So with the first model iteration, already users got some value from it and could do a basic statistics out of it. But whenever they look at a video, which they do a lot during the day, they always have the chance to just click one button and set a label because they find some interesting behavior, or just because they say, okay, I watched those 10 minutes now, I could just add this to our training data that will help the system. That's good. Or if they say, okay, I want to now specifically spend half an hour to improve our model, they can click on this smart assistant, get pointed to points of the video where our system thinks these are really the subsections that should be labeled, and then afterwards retrain the model and hopefully get better predictions. All right, now let's get a bit more technical and look at the machine learning methodology that is used under the hood. So for actually doing this behavior prediction, we have kind of a two-stage system. So from the raw input, we first do key point detection. Why? So for one point here, we can use transfer learning. So we can use key point detection models that are already out there for rodent data. Key point detection is kind of the task of identifying certain parts of a body in the video. So where's the nose, where's the tail, where are the ears? And this, in the end, kind of already extracts all relevant information from the video. So if you think about it from a data perspective, a video is a lot of data, right? It's a lot of pixels. And in the end, the information we care about is only concentrated around the body of the rodent. So that is the only information we kind of need to extract from one frame, and can then do the actual supervised learning with our tasks. So the task here being this behavior detection of rodents. We can then do it in this much smaller feature space in the end, because just if you could just think about the numbers that the model has as an input instead of raw pixel values, now you have something where also human domain knowledge can be involved, and it is much easier for the model to now train what is running, what is sleeping, and so on, because the input complexity is already very heavily reduced. And you use this transfer learning and this aspect of knowing which parts in the image is actually relevant for you for this task, to then need less labeled data to get good results. And then on this feature space, I talk a little bit more about that in a bit. Then here we just use XGBoost to do a classified supervised training to classify these predictions now on a frame-by-frame basis. But to calculate the features, there we have time windows so that we also have the temporal aspect in the approach. Did I miss something? Okay, yeah. Besides the key point, we detect also some other things in the image. For example, the cage area or where the feeder is. So that's then relevant to know if the rat is eating or not. So we extract some meta information from the frames and then information about the rodent. One aspect that I forgot about is this also makes it much easier to have this whole system where users can retrain models, because you don't ever need to touch the keyboard detection part again. The classifier, the XGBoost classifier that you retrain, this is very cheap and can be done very quickly. So this is another large advantage of the system. So once you extracted those features from the videos, now if you add more labels or if you add a new class, you only need to train the right part of the XGBoost, the right part of the system. So you only need to retrain the XGBoost model and do not do kind of something on 1,000 hours of video data, which would be computational much more complex. Okay, then let's talk a little bit about the features that we used for the XGBoost model to do the behavior classification. So we have in the end around 100 features, and they can be categorized in 3 areas. So one is kind of more global information of where is the rat positioned in the whole cage. So what is the distance to the center? What is the distance to the feeder? What is the distance to the corner points for certain key points, things like that. That's, for example, interesting, or you need this information also to know if the rat is eating or drinking, because then you have one feature that very heavily correlates to it. Then we have some features that try to extract the position of the body or the pose of the body. So instead of just feeding the raw XY or relative XY position of the key points, we have things like what is the distance from the center of the body to the nose? What is the distance from the nose to the tail base? Something like that. Where then, for example, if the rodent is sleeping, which means they are curled in kind of a croissant shape, then the nose is very close to the tail base. So again, you know which features you should look out for, and then you can design features that should hopefully correlate to also the behaviors that you want to specify. And the last one, this is now the temporal aspect that you also need to incorporate into your feature space. How is the movement of the rodent happening? So you use different rolling windows and then aggregate certain features for different window sizes. So just for example, was there a directed motion for every key point in one specific direction, or is it more this random movement? So then again, if you see, okay, in the last 1 second and in the last 3 seconds, the head of the rodent was moving in one direction, then you know, okay, probably the rodent was running, right? And was not sleeping, because then all the key points wouldn't really move a lot. So these are kind of the 3 type of categories that we use. And then there's, of course, a lot of experimentation that you can do with this feature space. You can then find correlations and reduce the amount of features that you have. But actually XGBoost is quite robust to this redundancy and figures it out on its own. But yeah, here you can kind of bring in your domain knowledge, your machine learning knowledge also. And yeah, this is kind of always a nice property of a machine learning system, I think, if you have an easy way to bring in your domain knowledge. Because in the end, if you can use the domain knowledge to design the system, you will always need less training data, because then there's a lot of information that the model doesn't need to learn by its own, because you already incorporated into the system design. Let me at this point maybe have a quick check at the questions. What are common challenges and how do you overcome in computer vision when running the inference on edge? So we actually are not doing on edge here. All of this is a cloud-based system. We cover this a bit more in the end. So that for us was not much of a problem. We could just use a NVIDIA GPU. But yeah, I'll dive into that part a bit more in the end when we look at the system details. How do you handle the temporal and spatial aspect of key points just with XGBoost? What's the reason for not using some sequential models such as LSTMs or GRU or even Transformer? Yeah, so two aspects. One thing is this, like now it's very cheap and quick to retrain this XGBoost model. You don't have to touch the video data again. And training on thousands of hours of video data, this is quite expensive and takes a lot of time. And if you want to have a system where users are encouraged to just every night or every day, because in the end it just takes 20 minutes to retrain that model, maybe they just put in 20 new labels for one new class, they click retrain, 20 minutes later they get the new results for thousands of hours of video material. So this is one nice aspect of it. But yeah, I think the other parts I mentioned now with this, here we can really bring in this domain knowledge, and learning this behavior from the raw video material, it's just a much harder task, and that's why you would need much more label data to do it. And first extracting information via the key point model and then only operating on this feature space makes it much more label efficient. Okay, then the annotation strategy. In the end, this was a really huge part of the project because the ML methodology we already kind of had before project start in our first proof of concept to prove to them that we can build the system. And we told them basically, look, we showed we have a machine learning methodology that can do this classification part. Now all we need is data, and we need the right data, meaning that also we need to discuss a lot with them. When should they add a new class? How do I ensure there is no overlap between the classes? And a big decision was also to say, should one frame of the video be able to only have one label, because a rat might also be eating and at the same time scratching or something like that? Or should we say single frame, only one possible label? And in the end, in this project, we always went for the more simple approach, or less complicated approach, and we felt like it was always the right decision. But okay, talking now a bit about how do we choose which labels, which areas to query a user to label. So we have 4 different strategies, and then we combine them equally. I think one of the most important one is predicted rare behaviors. So that means in the system, we know how much labeled data do we have for every class. And now we say, okay, which classes are underrepresented in our dataset, which ones do not have, or which ones have significantly less amount of data than other classes. And then we say, whenever a model predicts this class, this should always be labeled, because it is so difficult to get labeled data for this class if anywhere in this whole dataset the model was predicting this. And of course, in the beginning, it might be wrong. But yeah, we would always then pick those. Specifically, we would even pick it if it's in the top 5 or something like that. So You can imagine a user adds a new class. One thing they added was jumping. So the rat is jumping, and in a 14-hour video of a rat, the rat is maybe jumping 5 times, and one jump takes half a second or so. So again, for a human, or if you just randomly select the data, you will never get this class labeled. But they had 2 examples that they had labeled, and even with these 2 examples, the model would then, like, from all predictions of the model, we would take the predictions where the likelihood for jumping was the highest, even if it was still only 10%. But just from all they labeled, from all predicted samples, take the ones where the likelihood for the rare behavior is the highest. And that's how we were able to get much more and much quicker, more labeled data for these rare events and rare behaviors. The other one, this is kind of the default one. Everyone thinks about that one for active learning, uncertain predictions. So if the model was uncertain, then choose those examples, just because we expect that feedback to the model is quite helpful here. The next one is samples with high novelty score. So we had another algorithm that tries to define or tries to find samples that are different from the rest of our data set and would pick those. Again, from this user request of saying, it might be that the rat is doing something that has never been seen before. So we needed some algorithm that at least tries to find these ones. And again, like often, these were then also uncertain predictions, but not always. Like if you think about the decision boundary of the model, uncertain predictions are usually between 2 classes. But if you now end up in the feature space somewhere where you've never seen any sample, it can be that the model is extremely confident, but it just has never seen any sample with this feature distribution, and you just cannot trust the confidence there at all. But by measuring that it is far away from other samples, then you are able to still select it with this strategy. And the fourth part, also not to be underestimated, are random selection. So if you do active learning, and also if you look into the research in this area, the random baseline is actually also valid and strong, because it also guarantees you that you do not have any bias in your data labeling strategy, which can also be an issue. But that's why I would recommend always have at least one part just randomly selected, so that at least one part is selected without any bias. All right, looking a bit at the time, I think this novelty detection algorithm I have to go very quickly over, but I kind of already explained the main idea. You look in the feature space. In this case, now for visualization, at least we reduce it to 2 dimensions via PCA. And now you have a distribution for every labeled class in feature space. And now you select the samples that are far away from your from these distribution centers, with the idea these are samples that are far away from all our labeled data, and that's why they might show a new behavior, because they are different to the known behaviors. And that's would then get a high novelty score, and we would add this to the labeling queue. Okay, that was the machine learning part. Now let's talk a little bit about the tech stack and then wrap up the talk. So this whole system, how does it work? I mentioned already before, it's a cloud system. And then we use Kubernetes and Flight for orchestrating. So we have a Kubernetes cluster, we have some backend replicas serving front ends to the users. And if a user then clicks on model retraining, then we use Flight, orchestration pipeline that then starts the data pre-processing or training dataset creation task, then does the model training, and then does inference. Yeah, and we are pretty big fans of Flight. So this was really nice. You can define, okay, if I have this key point extraction model task, this one should have a GPU attached. Then for inference or for the XGBoost training, we just need CPUs, and you can pretty much nicely define that. You can launch these pipelines per hand also, this kind of stuff. Squirrel is actually we built this framework ourselves. It's open source, Squirrel Core. Go check it out. We use this one for data loading. The main idea is here that we create message pack format for sharded datasets parts so that you are not sending 1,000 requests to a bucket, but instead you have all of this data already compressed to one chunk and downloaded with a single request. 51, we also use that one a lot. We are big fans of that framework as well for video clip exploration. So where we used it mostly was for coming up with features. So we have the labeled dataset. We created a 51 dataset then of video snippets with the labels. Now you can sort in 51 and say, show me all snippets of eating. You get the nice dashboard of different snippets of the rat eating. And you realize, okay, of course, the rat is always close to the feeder. Maybe we should add this explicitly as a feature. And 1 dB for machine learning development, just to track the experiments. Yeah, and then the two pipelines that we had was one, users upload new videos. Then we have a cron job that looks for if there is a new video in the video bucket, then it runs the key point estimation. Deep Lab Cut is a very good framework for that. It's specifically designed for dealing with this, like rats, for example, key point detection of rat data, feature generation, model inference, and then if a user clicks model retraining and selects which classes should be selected, model training and model inference. Okay, almost done. Results. So this is a confusion matrix. You can see that a lot of classes are very good and some classes don't work at all. So these are usually the ones that are either very rare, so where we just don't have a lot of examples, or they are classes that are where the key point stuff is maybe a bit of a disadvantage, or also just the video quality is low, and even for a human it's hard to see. For example, digging, a human usually recognizes digging because then you can really see the pause, but we didn't track the pause explicitly at key points. That's why digging is a bit difficult to detect. But in general, for a lot of classes, the system works very well, and that means that it provides a lot of value for the users to then identify, jump to a specific part in the videos, get these statistics that are meaningful to them. Yeah. Okay, the last slide, kind of a bit of a wrap up of the whole approach, and then maybe I have 1 or 2 minutes left to go through the questions. Again, if we think about the whole loop that is happening here is a user uploads data, we check for novel behavior with this distance in feature space. We run inference automatically and then get also this uncertainty estimates and predictions that we can use to then again tell the user, look, you uploaded a new video, maybe go through this queue. You can just click through, the video jumps to the sections and it will contain possible rare behavior. It will contain possibly new behavior and behaviors where the model was very uncertain. The users can now confirm the predictions, or they say this is new, I add a new class. They click retraining. Now the model knows these new classes a bit better, and it's better at identifying where in the video this new behavior is happening, and the loop kind of continues. And yeah, it was a super cool project because it was all different parts, from key point estimation to how do I get a cloud flight pipeline to work, to how do I explain to a user why this and this with machine learning is not possible. So very cool project. We also wrote a paper, a workshop paper at ICML. So here's the QR link if you want to read more about it. Okay, I'll spend maybe 2 minutes, if that's okay, to go through some questions. So Mike asked, can you induce rules of behavior perhaps with LLMs? I think it's mostly supervised. Yeah, it's an interesting idea. Can you use the LLM feature space or in general also LLMs to help you with suggesting which parts to label or even to identify it? Would be really cool to go more into that and actually explore it. I think there's definitely huge potential. I think generally with this, you're in a new domain, and if you are somehow able to map it into a embedding space where LLMs can operate and use all of this, yeah, pre-training that in the end happens with LLMs to extract information from your data, I think this is very, very interesting for the future. How large was the data set you trained on? Which pre-trained models did you try and use for the key point detection? And how long did it take to train the XGBoost? Data set, we started originally, as I mentioned, with half an hour of labeled data. The key point model, we used one that was provided by this deep lab cut, but we had to fine tune it on our data set, but that was very easy. So we just labeled maybe 70 frames, something like that. And then the key point model was working well, and we just didn't spend more time into optimizing it. So that was very easy to get to run. XGBoost runs through very quickly, and then every week we add more labeled data. I don't really know how much hours or how many snippets separately we have, but probably a factor 10 more, so maybe something like 5-6 hours now. How many key points did you use? You saw it on the picture, I think something like 7 or 8. Yeah, I don't think you really need much more. How much would all of this cost? Send me a message about that. We can also sell this system to other people. I don't want to answer that more here, but we can totally talk about it if someone is interested. Where do you store inference results? Yeah, that's a good question. So the feature store, the features we had extracted, we store them in a bucket as feather files. So basically pandas data frames. But then the inference results we store in a database, Postgres. And then the active learning part is actually SQL queries. So you query from all your snippets. So in the database, we don't store it as frame by frame, but as start and end. So it can be like 2-3 seconds of one behavior. And then you have these queries for like, from all my snippets, give me the ones where the uncertainty is the highest, or give me the ones where this and this class is predicted. Also, so that users can say, I want to click through all events where the red is jumping. Then you have the query to the backend, give me all snippets where jumping was predicted. So this stuff is then stored in in a backend, in a Postgres database. Would YOLO be useful also for classification? Yeah, I think YOLO for classification. I'm not sure how exactly you would do it. I think here for the classification part, the temporal aspect is really important. So anything that only looks at one frame will have difficulties. I don't know if there's a solution for YOLO as an input for video and then you put it out. But I mean, generally, there are systems that are at least similar to it that operate end to end directly on the video data. Yeah, but as I said, end to end has a lot of disadvantages. Do you think using CG simulated data can play an important part in this? So we didn't really think much about synthetic data just because we had such a large amount of labeled data. Yeah, I think in a lot of other projects, it's definitely interesting. In our case, I think we didn't really see a need for it. All right. I hope you found the talk interesting. Sorry for being a few minutes, maybe over time. If you have more questions, read the paper or reach out to me. And with that, that was it from my side. Thanks for the attention.